by 10. So 5 by 10. Man, this question was easy.
Okay, good morning to everyone.
And Mama?
Hello, all of you are there.
Good morning, sir.
Morning.
Yes, sir.
All right, so today we will try to learn the third IPC mechanism, the semaphore objects that are actually used for synchronizing multiple processes. Right, so whenever you want to access a common resource and multiple processes want to access a common resource so that a controlled access is required, whereby only one process is allowed to access that and others must wait even if they would like to. So such kind of synchronization is possible by using semaphore facilities. Right, so here you have three system calls, and as you can see you have to include the sys/sem.h, first three letters of the semaphore. So there are three system calls related to this. As usual, one of them, the very first one, is going to be semget. We use semget in order to create a semaphore and start using it. It returns an ID as usual. And like in the case of the semget, what are the parameters you are passing on? As usual, the first one is the key value. And all the processes, whichever would like to work on the same common resource, will be using the same key value. And how many semaphores are you interested in? Number of semaphores. Many a times it is likely to be a one semaphore, but if you want, you can also have a facility whereby you can create a set of semaphores. And the third one is the flags, permissions, and then whether you want to create at the time of getting the semaphore and all that, those flags as usual, you require that. So semget is a simple mechanism where you pass on the key value, how many semaphores are you interested, and the flags to create the semaphore and all that. Right? So, and then you have another one which is called semctl. The semctl is actually used to initialize the semaphore with any particular value. One of the objective actually. TTL, as usual, if you want to remove the semaphore, ultimately after the usage, you have one command for that, IPC RMID. Similarly, if you want to initialize a semaphore with a starting value, we use semctl for that, right? So that is one of the important things. There are many other commands there as a part of that. Here he has given probably one or two, but the actual manual suggests many more things. Anyhow, so this command parameters for that are going to be, the first one is going to be semaphore ID, and then the semaphore number. What is the number on which you want to work on? Right. The second one is the semaphore number. There may be like multiple semaphores. As you can see, number of semaphores, how many you want at the time of creating. So which semaphore on which you are actually trying to control, in other words, right? So you can specify the semaphore number, and after that the command, and then the additional data that is required for running that particular command. Running that particular command. This dot means there can be, it is a variable number of arguments. Three dots means variable number of arguments. It takes like some more additional parameters depending upon the command. So that is about semctl. We'll slowly come to that. And then the semop is there, using which you try to synchronize. You try to get access to that common resource by running some of the like a semaphore operations like a P and V actually, or wait and signal kind of thing. Like in the sense that like how many resources are there right now in order to use it. In case there is only one resource, maybe one. If it is already in use by somebody else, it becomes zero actually. So you want to get access to that. Naturally, you can get access to that provided there is a resource. So based on the value of the resource, like value of the semaphore, you are actually going to permit it to access the what you call critical section code and all that. For that, probably we can take a look into the general theory behind that particular thing. Semaphore definition, as you can see, you have binary semaphores and you have general semaphores. Simplest semaphore is a variable that can take only the value zeros and ones.
Ma'am, I have done it in the same way.
Such semaphores are called as binary semaphores. This is the most common form anyhow. Semaphores that can take many positive values are called general semaphores. They are also sometimes called as counting semaphores. So he is actually talking about only binary semaphores for only 0 and 1 are the possible values for the variable. So the kind of operations that are permitted on these semaphore variables are one is P and the other one is V. What is important and the beauty of this is that these operations are atomic in nature. Either P of SV is going to be started, and if at all it is started, it is going to be completed, or it is not going to be done at all. If you start, it is going to be completed. If you don't start, or you can stop it. That's what we mean by. So there is nothing like half of the code of P of SV is going to be executed and then give access to some other process. It is that particular problem actually. That's the reason why all these semaphore synchronization is required. Because when you are running multiple processes, the operating system has got the control to switch the central processing unit between the processes. You can switch between the processes anywhere for that matter. So if you switch the processes like that, then essentially critical section areas and all that, there is a likely problem, right? So of going a particular variable taking some inconsistent state and all that. You must have studied in database management also, where like how do you control access to that concurrency mechanism and all that particular thing. Critical section code, operating system also you must have studied. So P of SV means you are waiting, it is equivalent to wait actually. Wait for SV to become greater than 0. That's what you mean. If SV is greater than 0, then it will directly proceed actually. So it is decrementing the value of it, and then if SV is 0, suspend the execution of this particular process. So one of these two actually. If SV is 0, it keeps waiting until SV becomes 1. What do you mean by SV is 0 here indirectly? The resource is already in use by some other process. The resource is already in use by some other process whenever this semaphore variable value is 0 actually. If it is 1, it means that the resource is available. So, so what do you do whenever it is 1 and you want to access that? So you will change that SV value to become 0 so that nobody else can enter into that. So that's what, right, P of SV means. It's a waiting one. Whereas V of SV means signal. That means a process that has used a resource after the using, it wants to now allow any other waiting process. How do you allow waiting process to start using this resource? By changing the value of the semaphore value. So V of SV, you increase. This is not going to be waiting actually. It will proceed. If some other process has been suspended waiting for SV, make it resume execution. That's what you mean. You are allowing other processes that are waiting on this SV to proceed further. If no process is suspended waiting for this, simply increase the value of SV. Actually, indirectly, you are increasing the value of SV, strictly speaking. And then it is the other process that can actually probably, there may be competing processes, one of them is allowed and that is going to decrease the value of SV by 1 so that it becomes 0. So P of SV and V of SV or signal and like what you call wait kind of thing. You can see here critical section code how you can write the general code. You see here semaphore SV equal to 1. That means one resource is available. That's what you mean, right? Imagine as if this code is executed by many processes concurrently, parallel. If many processes are executing the same code, how do you ensure that this particular critical code, section code, is allowed by only one process? Other areas like non-critical code section here, there may be many lines of code here. In this area, all the processes can be there. But this is the one that you are actually trying to control. Right? Important thing is about giving access to critical section code. Only one process should be allowed to be in that particular area. No matter like at what speed processes are running, no matter what kind of scheduling algorithms operating system uses. So this particular code will ensure that the critical section code, only one process is going to be there at any point of time. How are you controlling that? If you see, you are using a semaphore variable. It is a forever loop. And then now, even if there are multiple processes that are running at the same time, only one of them is going to be successfully in executing P of SV. Because just now we said P of SV, either it is going to be completed so that right you can move on to the next step, or it doesn't start at all. Right? So you are not going to stop in the middle actually. Once you begin the code execution of P of SV, it is going to be completed. Atomicity, that is what is called as atomicity. You do not break the execution of the code of a particular instruction, function, or any one thing, what you call it. So what are you doing here? Before entering here, every process is verifying. He is trying to get access to that common resource. But only one of them will be successful. And the one that is successful will go into critical section. And all the other fellows naturally are waiting there now, whoever are there, or might be in the non-critical section. Once this fellow completes the critical section, now what he is going to do? He is again going to increase the value of the semaphore variable by 1. P of SV means actually it is equivalent to decreasing SV by 1. Right now it is 1 initially. The moment the P of SV is successful, SV becomes 0 actually. SV is going to be SV minus 1. So it becomes 0. So while that process is executing the critical section code, the value of SV is 0. And many processes are waiting. Now after the usage of this fellow, what he is doing, he is increasing the value of SV by 1. So that So that because this fellow already has completed usage of the critical section code. And even if you want to again give it, again want to run that, he will go through trying to get access to that P of SV. So if the moment he says V of SV, then one of the waiting processes, there may be many processes, but only one among them will be successful based on the operating system, your scheduler and all that. Only one will be successful in doing that particular. So, so that's how it is. And this fellow can go on to executing the non-critical section code, whatever is there. So, and again goes on like this. So, this is the principle actually behind it. So, this is a general theory, but now this P and V can be implemented by using the semaphores in our those system calls like semget, semop, and semctl. You don't have directly a function like P and a function like V. That's not the way. Only in theory you are actually talking about. There are some other, in some other languages, these things were tested out, especially in Algol and all that. Right? So Algol language provides these things as it is. But the question is now C language doesn't support this kind of semaphore straight away. But the Linux is supporting the corresponding concept using the system calls like semget, semop, and semctl. So there, like here, this is only a single variable, a single semaphore. Whereas semget, semop will operate on, can operate on a set of semaphores. A set of semaphores. That's called a semaphore set. So the concept is slightly different. The idea is ultimately the same. But the parameters, it's not a variable kind of thing. There are some languages where semaphore can be declared as just like you say int followed by x. You can say semaphore followed by x. But that's not possible in C language. So for that, what you are actually doing is, this is another diagrammatic approach, whatever, same idea. Remember, this is the critical section code. So before entering into the critical section, you are running this P of semaphore, and then use it, and then update it, non-critical section and all that. So P on semaphore, only a single thread of execution can enter the critical section at any point of non-critical section of process P, and this is process P and all that is actually going into that. Anyhow, so this is what it is, like the semctl is used in order to initialize the semaphore with a particular value. After initialization, the semops will come. In this semop, you have the facility to perform either V operation or perform the P operation. That is possible based on the kind of value that you actually pass on. Semop of ID and struct sembuff star semops. So an array is going to be provided here because a semaphore set, there may be multiple things. So, and then after that, how many operations, number of semaphore operations that are to be performed. This depends upon how many entries you are actually passing on here, right? So this sembuff will contain actually the fields responsible for performing either P operation or V operation. We will look into that particular thing by just going through the code and all that. This is straightforward, as you can see, semget, key value, how many semaphores and flags. It is straight away, there is no complexity here that is involved in understanding these things. But semop now, while performing the sem operation, there is struct sembuff, and what are the fields within this sembuff? These are the fields. Right? So, on which semaphore you want to act on, that is indicated by the first field, semaphore number. Because there is a semaphore set, right? There are so many semaphores. And always the semaphore numbers begin with 0 actually. Just like the array indices starts with 0, semaphore numbers begin with 0. Semaphore number 0, number 1, number 2, and so on like that. And on this semaphore number, what is the operation? Right? That operation is indicated by second parameter. And it is a short integer, as you can see. So if semop is +1, it is equivalent to V. If semop is -1, it is equivalent to P operator. Because you want to reduce, you want to get access to one resource. You indicate your interest to access one resource by initializing this semop with -1. When you say -1, the value of the number of semaphores is going to be reduced by 1, or the number of resources will be reduced by 1. Or at the end of the usage, you again increase it by 1. So the semop is going to be either +1 or -1. Remember that. And sem flag is there, whether you want to, as you know, semop, it is a waiting or blocking system call. Because if the resource is not available and you are asking for a resource, you will be waiting. So that's why whether you want to wait or you don't want to wait and only find out whether is it possible kind of thing. That is possible by using sem flag. IPC no wait, such kind of thing is possible. The other one is actually another important thing is sem underscore undo. This flag is likely to be initialized with sem underscore undo actually. Meaning that like you are running a program and the process abruptly is terminated for some reason, let us say. So what happens to the semaphore and the operations and all that, right? So, so many other processes are going to be waiting forever. So in such cases, if you initialize the sem flag with sem undo, operating system will take care of like proper closure of the semaphore. It's going to remove the semaphore so that all the other processes are going to be also wind up, kind of. So most of the time, for simple your understanding, sem flag is going to be sem underscore undo. Remember that. So that's all. It is semop is as simple as this. And then semctl is already we have seen. An ID is to be passed. And what is the number on which you want to work on? Semaphore number command. The command can be set value. Set the value of a semaphore. Because you want to initialize it. So after the command, what value you want to initialize is indicated by this union semaphore union. Remember that. It's not a structure, but it is a union. Union, sem curly brace begin. Of which you are actually specifying int val and then struct semid underscore ds star bus unsigned short star array. So 3 fields are there. But all these 3 fields will have the same sorting answer. Only one of them will be meaningful in fact. Either you are going to use for some one particular command val is going to be used. For a different command buff is going to be used. For another different command array is going to be used. That's why they are using actually union mechanism. That is the advantage of union. It doesn't take more space. It is going to all the fields within the union. Their starting address will all be same. Because at any point of time, only one among them will be in use. That you have to understand. If it is a structure, you create a space for all the fields. Whereas for a union, you create the space only for the largest possible fields within this. Because every field starts with the same address, same starting address. So we can see here there is something called set val. Set val is one of the commands. IPC RMID is another command. But there are actually other many other things like you want to get the corresponding details, you want to set all the values of that. Like that, there are many other things also. If you want, you can just take a look into this particular thing. Then you understand actually. Either this or that. This is semaphore, right? So this is one, like if you just take a look into this, what are the other possibilities and all that, complete thing, which is there in tldp.org. In one of the earlier classes I told you, in fact, this link. So semctl, these are the parameters, but the command, if you see, even though in the textbook only two things are there, just I am specifying, but try to learn at least up to whatever is given in the textbook. But the question is, all these other possible commands are also there. IPC stack. So this we have seen even against the shared memory and other things also. So that you are going to get the details about this particular semaphore. IPC statistics, that's what we mean. So there is a data structure, semaphore data structure here, and that is going to be filled with all the details. So IPC underscore set in order to set a specific value. Right? So you can set the permissions there and all that. All the values of all the get all values of all semaphores. That is possible by using get all. It returns an array of values. Like that. So get value of a single semaphore, you can see get val. Just like you have seen set val. This is the one that is being used in the text. Instead of initializing a single semaphore, you want to initialize all the semaphores, you can do all of them at once by using set all. So those things are possible there. You can just take a look into that later on. Coming back to this now. So this is what it is. Set val and IPC RMID. These are the two commands. Now we can, by just taking a look into the program, you will understand like how you can use this, what is the purpose of that, and so on.
Or you can have more than one.
Okay, so there is only one program now. Remember that the semaphores are not meant for developing client-server programs. You are not passing any data here. What is the objective of a semaphore? To synchronize access to a critical section. So semaphores will not receive something and will not send something. There is no communication and all such kind of thing. So if at all there is a shared memory, for example, then that shared memory should not be allowed straight away by multiple processes because the data is going to be inconsistent in such a case. So there, access to that common resource like shared memory is a controlled manner by using a semaphore as well. So you will use semaphore coupled with shared memory. So that kind of programs you will see, producer consumer programs or whatever, right? So in this case, it is a very simple example we are actually going to talk about. So include all the header files, whatever are required, and what it is, semun.h. So essentially, semaphore union is like what is going to be there within that semaphore union. So semun, you can see there like what is going to be included into that particular thing, like here. So this is one like a thing. This is a semaphore union, right? So this is one entity, usually some set. So have a definition of the SEM union in a listing. In case it's not there, we'll have to do it on our own. So this is going to be kept there as a part of it. So let us see here. What are the header files anyhow, you'll have to include it. Now what we are doing is, we are trying to simplify by developing certain useful functions. Certain useful functions. What are the functions you are developing in there? One function is going to take care of initializing the semaphore. And that function is called a set sem value. Right? So that simply make a call onto that, it's going to initialize the semaphore with a known, with one whatever. So it's simplifying that basically. Set sem value is one function. Similarly, delete sem value is another function by which you are going to remove the semaphore by using IPC RMID mechanism. And there is another function called semaphore underscore p. This is a wait mechanism. You want to get access to a common resource or critical section, right? So that is called a semaphore underscore p. Similarly, at the end of the usage, you want to give it back, right? So you say semaphore underscore b. So these are the four functions that we will be developing by using those three system calls. And as you know, because these functions require what is the semaphore on which you are acting on. So instead of passing a parameter, he is making it as a global variable. He is declaring the variable outside the main. That's why it becomes a global. So that the stem ID is accessible both in the main function and also in all these four functions. Stem ID is accessible everywhere. That's what you are actually doing. Not a good practice. It should have been it is better to pass that as a parameter than it would have been much better in fact. But it's okay. Sometimes people think along these lines also. So this is a global variable. Static int, stem ID. Now int main of RC and character R. Command line R. Int I, some integer variable. Pass time, how much pass time? You see there, critical section and a non-critical section. Two areas are there. How do you simulate it? Critical section means imagine there is some code, but to run that it takes some time, right? So you are actually going to have some sleep kind of thing. Critical section, you introduce some sleep, this many number of seconds. Non-critical area, some random number of seconds you are going to sleep there. The other day also we have designed for shared memory and other things along those lines, right? So how much should be the pass time? That's what you mean. And then here what he is doing is, whether your program is correctly working or not, is tested by printing two characters. Before entering the critical section, you print one character. Right? Before entering the critical section, you print one character. After completing the critical section, you print the same character. You print the same character. So, one of the process is going to print one character. A different process will print different characters. Like in this case, actually, one is capital O, the other one is capital X. One process will print O, another process will print X. If the program works properly, it will always print O, XX kind of thing. It will never print O followed by X or X followed by O. What do you mean by O followed by X means? So the process with O is entering into the critical section. Process with X also is entering into the critical section. If both of them are printed simultaneously. But if you say O and O, what do you mean by that? O process enters into the critical section. And after that, like the other one is not allowed. So another O has come means it has completed. It has completed the critical section. So it's printing another O. So like that, you are actually trying to test this particular logic. So for that, some random time you want to sleep. So for that random number, you are actually working on. So first initialize it, random number generator with a seed. So yes rand of get PID. So you are initializing the random number generator with a seed actually. That is what you are doing here. Later, you will generate a random value between some minimum and maximum this thing and then sleep for that much duration. These things are not so important, but anyhow, for the working of the program, you require that, definitely. So semget now. Semget of 1, 2, 3, 4. How many semaphores you want? One semaphore. Only one semaphore is asking for. Permissions are there, and it should also be created if it is not already there. Simple. So it returns a semaphore ID. Right? So how do you distinguish between one process printing O, another process printing X? That you distinguish based on whether you are running the program with the command line argument or without command line argument. If you run this without command line argument, you will have capital O there. If you run with command line argument, then that process will print capital X. That is the difference actually. That's why here he is verifying if RC is greater than 1. Are you running this program with a command line argument? If it is, then only that particular thing is actually he is creating the semaphore. Remember that. So the command with a command line argument, he is going to create the semaphore and start running it. If you run this without a command line argument, it doesn't create. It will try to use the existing semaphore. So that's why after the usage of this, you have to first run the program with a command line argument and run the same program once again without command line argument. We'll look at that. Right? So if RC is greater than 1, what are you doing? You are creating the semaphore. That's what you are doing. This set sem value will create a semaphore actually. Remember that. We'll see there, like if the function will come a little later. So this function, if it is successful, it returns 1. If it fails, it returns 0 actually. So whenever set sem value for some reason fails, it returns 0. So not 0 means it becomes true, so it has failed. So whenever it fails, take care of the failing mechanism. If it is successful, it will come to this particular point. So semaphore is created, right? Semaphore is created. So that's why, and it is also maybe initialized with 1 value. That's what we mean by op character equal to X here. See, earlier it was O, and now inside it is X actually. And then sleep for certain duration, sleep 2, and then curly brace 8. Now here, about 10 times, like both the processes are going to enter into critical section, get out of that, enter, get out, enter, get out, and so on. So several times, these two processes are competing. Even then, like we should not see a situation where both of them will be in the critical section. It should not be. So how are you going to do that? For I equal to 0, I less than 10, I plus plus. So first, as usual, before entering into the critical section, what do? P of A. So that's why you are saying means you are trying to get access to the common resource or critical section. Number underscore P returns 0. If it fails, returns 1. If it is successful. Remember that. If it is successful, it returns 1. If it is failed, it returns 0. Failure case, take care of terminating the program. Take this. Successful case, what do you mean? So that means you have got now access to the common resource. Now you are printing the character. Print F %C of cat and F plus out STD out. So that this OP underscore cat is going to be different for 2 programs. For one program it is X, for another program it is O actually. So one of them is now entering into this. So it is printing this. Now from this point onwards, unless this fellow completes this entire thing, no other process is allowed to enter into critical. So it is printing that, and then it is waiting. This is the critical section time. You imagine as if these 2 lines stand for the critical section actually. So you are using the rand mod 3. Rand mod 3 returns 0 to 2. So how much time you want to sleep? So you say sleep of past time. Either 0 seconds, 1 second, or 2 seconds. Random. And again print the same character. So what we say is that we are guaranteeing that this character and this character will be the same. In between, no other fellow is actually allowed. Right. So again, now we are printing. After this, now what is to be done? We should allow other process also to enter. So we have run this P code, and after that you should run V code. So you say here, if not semaphore V, Semaphore V also again returns 0 and 1. 0 means it has failed for some reason, so you terminate that. 1 means it has successful. So if it is successful, you move on. So this area is equivalent to your non-critical section 4. Non-critical section. So here again, how you are simulating by using a random waiting time. So past time is random mod 2. These numbers, it is up to you. You can change, no issue. But the behavior will be same. 3 here and 2 here. And you can change. You can experiment, no wrong. So 3 for past. And again it goes back. Like this, both the processes will try to compete at random times. And always it is going to be in a proper way. They will enter into the critical section. That's what you really mean. So ultimately, after 10 times, you are just simply saying finish. Which process is finished? You also print it, get PI. So that you know whether the process with O or process with X, which is actually finished. But you can also say here, in fact, OP character also. OP char also, which you have printed. So that you know that that particular thing is finished. So if RC is greater than 1, what do you mean by that? It is that particular process that has created the semaphore actually. It is the process that has created the semaphore. He is waiting for a little bit more time so that other process will also complete its task. And then ultimately remove the semaphore object completely. So it is actually waiting for 10 seconds. And then you are removing the semaphore. Tell underscore semget. That function is there, right? Which are actually and ultimately exit. So this is the actual main program. Now all those functions you have to write. Remember that. You see, static int set underscore some value void. So what is the purpose of this? The purpose of this is to initialize the semaphore with a value equal to 1. To initialize a semaphore, what do? We use the semctl. We use the semctl to initialize that. And you can see here, for that you require semctl. Whenever you use, there is a union, union some union is there, right? Union some union. And this is a variable. Because if we want to initialize that, so use the val field within that. There already I said only one of those 3 fields will be used based on the command actually. For setting the value is important. So you are initializing the value. So sem union dot value equal to 1. This is the purpose of is to initialize the semaphore before the usage with a value equal to 1. So you can see here if semctl of some id comma, which semaphore you want to initialize. This second parameter is the which semaphore. It is a 0th semaphore. Semaphore number exactly. So you are initializing the 0th semaphore with a value equal to 1. So you say sem id 0 comma set val comma and sem union. Sem union. So sem union is there. And if this entire thing is returns for some reason -1, that means it has failed. It could not initialize. So it is returning 0. If it is successful, it returns 1. Simple. Right? So initialization of the semaphore is done by using semctl. For that you are using the union sem union. And this variable name, it is up to you. This is a variable name. Whereas this is a union definition. Right? So this is how you initialize the semaphore in the beginning. After this, what? You want to delete the semaphore. Deleting also you use the semctl only with the command name as IPC RMI. That we can see here straight away. Very simple. Static void del underscore some value of void. And then what? Union, sem union, sem underscore union. Here, because while removing, you don't require any data to be initialized. Right? So just like that it is there actually, strictly speaking. You don't need anything. But you are declaring this and then what? Semctl of sem id. And then here, this also, because it so happened, semaphore number and all that, these are meaningless, strictly speaking. But it is a more generic one because of which all these things are there. So anyhow, So this is going to, you can put any number here, but what is important is the command, IPC underscore RMI. And here, the following one is semut. You don't have to initialize anything there and all that. Because IPC RMID means it is removed in the entire semaphore. So these parameters are redundant, just like because of the syntax they are provided. So you say here 0, simply declare a variable and then pass on that particular variable. For some reason, if it returns -1, that means it has failed. It has failed. But we are not taking care of that, whether you are failed or not and all that. As you can see there, go into the code, then you will understand. See here, del underscore sum value. We are not
So 40
examining what is the return value of that and so on. So much logic he has not put. Whereas for all the other functions, either they are going to be successful and they return 1, and they are failed, they return 0. Based on that, we have already developed the logic. So, deletion is a straightforward, simple mechanism. Now, semaphore underscore p, it returns integer, as you know. P means what? You have to reduce the value of that by 1. So that's why, as you can see, declares now semaphore buffer, struct sembuff, and a variable. Initialize all of them with proper value. Semb.sem4 number. Which semaphore you want to control now? 0th semaphore. There is only one semaphore, and that is the 0th one. Because it is P means what? You want to reduce it by 1. Semaphore value must be reduced by 1. So semb.sem operation equal to what? -1. -1 whenever you want to perform P operation. Flag value is always sem underscore undo one. No issue. This is always fixed. So after initializing the sembuff variable, make a call onto semop. If semop of semaphore ID, pass on the starting address, ampersand semaphore buffer, and how many semaphores are you actually initializing? Only 1, right? So that's why you say 1. But in case you are working on 2, 3 semaphores, then depending upon how many, that many number of entries must be initialized, and then here you have to specify the number. Right now it is only 1. So ampersand semb, 1. Only one operation, this particular operation, of reducing the 0th semaphore by 1. That is the task. If it returns for some reason -1, there is an error. So you return 0 by printing the error message. If it is successful, then you say return 1. Already the job is done here. But to communicate the calling function, you are saying that yes, I have done the job. So you say return 1. Here, you have not done the job, whatever is asked. So you are returning 0. That is how it is. Simple actually. Semaphore P is like this. Similarly, semaphore V, same logic, only this is going to be changed. The -1, it's going to be +1. Because you are now increasing the value of it. So, semaphore V and struct sembuff underscore B, and then you are initializing. Which semaphore? 0th one. Operation is going to be +1, undo, and then all that. Same thing. That's all. Like as far as this is concerned, after that, what do? You compile it. Then you have to run this actually. Just now we said you run the command in the beginning with command line argument, because the command with command line argument will only create the semaphore. So that's why you are running this particular thing with ./sem1 followed by this. This can be anything. It doesn't take whether you are giving 1 or ABC or some junk, whatever you give, it doesn't matter. Only thing is there should be one argument at least. It can be even 2, 3 arguments also. He doesn't even go into that. So he is distinguishing between two processes, whether with a command line argument or without that. That's all what he is actually talking about. So the moment you run that, you have this 1 followed by 1082, whatever. And then run another command, same thing, without the argument. Now the moment it's over, as you can see, some output, you may not get the same output, remember. But what is important is, once a a letter O is printed, letter X should not come immediately. If both of them are coming, then there is a race. First process has got into critical section, and even before the completion of that, second process also is getting into that. That is a wrong code, right? So here, so you are verifying XX, 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 like that. And here it so happened one time, and another time also the same process is getting. Another time also same process is getting. All those things are possible because those random times are there. Probably X is waiting here for in the non-critical section. So if it is waiting for more time, then within that this process with O might have completed and again come back, and the same process is getting a chance to enter into the critical section. Right? So after some time anyhow here also you can see X also is getting O. So this is how it is, semaphores and all that. We can just take a look into the code here. This is the same thing I have taken into the like an editor, and you can see here these are the things. Hash includes semun.h. So what is there in semun.h? I will show you. So this is the one. Union semun. And then integer val. As you can see here, this particular value field is used for the command like setval. And the buffer data structure is used for the commands like IPC start. So whenever you say IPC start, then this particular data structure buff is going to be filled with permissions and all those things, whatever are there. Or you actually initialize this buffer with values and then ask it to set by using IPC underscore set. But for the command like get all and set all, they will use this particular way, array way. In this array, you will have all the values. What should be the initialization value for the first semaphore? That will be there in array of 0. Second semaphore value, array of 1. Third value, array of 2, like that. So instead of calling this set val so many times, you can call set all and then initialize all of them with a single command. That is the purpose of that. And then other additional IPC info and all that, this particular. So these three are important. Now you can come back to this. So these are the things, anyhow. Okay, so the same program, essentially, let me just show you, even when you run the program also, unless you understand, you don't get a feel. So now you can say /sum1. But with some data, right? Some junk, it doesn't matter, but run this in the background because you want to run two programs. So you can see that it's going on. Already it has started. See there, it's going on. Even if you don't give that and all. How you run this like this. So maybe some other junk data. Okay. So already so this one actually are some value we can always and then do this. Zero. So now you can see XX, XX, like that, and so on, right? So number is that they are going to run. Whereas you don't put that semaphore P and semaphore V, then you are likely to get, in fact, both the things going into parallel kind of. So with this, the IPC mechanism we are actually done with, and now only what is the remote method invocation RMI is there. Probably in the next class we can just take a look into that particular RMI mechanism. So hope you are following that, and maybe just take a look into that and try it out. Okay. So, so any questions otherwise? Can we close the session?